Hi, my name is Alan Surna.
Hello, my name is Simon.
Hi, my name is Kobir.
Hello, I'm Fahmi. We are from Group 4. We'll be presenting the mechanics of materials learning outcomes in the selected biomedical device, which is lead pull-down exercise. Have you watched Daryl doing the exercise? Did you know what is the LPD or lead pull-down exercise is actually for? So let me explain to you. The LPD exercise, or we call that as leg pull down exercise, is a strength training exercise designed to develop the broadest muscle in our back, which we call that as the latissimus dorsi muscle. It performs the function of downward rotation and depression of the scapulae, back here, combined with adduction and extension of the shoulder joint. LPD machine also used as rehabilitation training for these three types of diseases, which needed muscle training, which are the cerebral palsy, scoliosis, and spinal cord injuries, because leg pull down machine can help to enhance the spinal stability and promotes good posture. So we will explain the three learning outcomes in the leg pull down exercise machine. The first learning outcome will be solve problems involving a body under the action of axial and torsional load. Axial loading, known as normal stress, which can inform of compression or extension. Torsional load is external shearing stress and shearing strains due to the twisting. Second, LO, solve problems involving stress in beams. And the last one is evaluate stress and information of biomedical devices, which is in our case is the LPD, lead pull down device, lead pull down machines due to a compound load. For the parameters measurement, we use the vernier caliper to measure the diameter of the object and the measuring tape for length. For the weightage, Daryl used 8 blocks of load, so one block equal to 1 kilogram, which is equal to 10 Newton. So 8 blocks equal to 80 Newton. So this is the picture of Daryl when he pulling the leg pull down cable. So let's find out the free body diagram of this picture. This is the free body diagram of the picture before. So this will be the guide for all my team members to do the equation from LO1 to LO3.
So today I'll be talking about the first learning outcome, LO1, which is solve problems involving a body under the action of axial and torsional load. So first of all, we have axial loading. So when the stay wire is being pulled down, it will undergo a stress. So we're going to calculate the stress in the stay wire at area A. So first, the parameters that we'll be working with is the load weight, W is 80 newtons, and the stay wire diameter, which is D equals 0.44 cm. So first of all, let's draw the free body diagram of the stay wire. So the P is equals to 80 newton, which is the load weight, and the area A is the area of the section cut of the stay wire. So let's first find the area of the A. So first we convert the cm into millimeter, and then after that we find the area of the circle A, which is 50.205 millimeter squared. After finding the area, we can find the normal stress that is experienced at area A, which is the normal stress is equal to sigma equals to P over A, and the result we get is 5.26 megapascal. So moving on, I'll be talking about torsional loading. Torsional loading occurs when the steel wire is being pulled down and it will experience a twist. So the parameters that we'll be using in the calculations here is the steel wire diameter again, D equals to 0.44 cm, and the maximum allowable stress, which is tau max equals to 50 megapascal. So first and foremost, we need to draw the free body diagram when the steel wire is being twisted. So that's the free body diagram when the steel wire is being twisted, as denoted by the top there. So we need to find the radius because we'll be using it later in our calculations. So the steel wire radius is we find is that it is 0.0022 meter. After that, we need to find the polar moment of inertia, which is J equals to pi r to the power 4 over 2. That formula is used for solid circular shafts, and the result we get is 3.6797 times 10 to the power negative 11 meter to the power of 4. So last but not least, we can finally find the torque, which is T equals to tau max J over R. So in the end, we get 0.8363 Newton meter. So that's all for LO1.
3. Moving on to the second learning outcome, which requires us to solve problems involving stressing beams. Today, I would like to talk about the methodology of LO2 and assumptions that should be made in order to solve the problem. First of all, the free body diagram is constructed like the one below. Secondly, the moment inertia was calculated by using the following formula: I equal to 1 over 4 pi c to the power of 4. Then, we consider the summations of moment is 0 to calculate the bending moments of the beam. After obtaining the moment of inertia and bending moment, the maximum bending stress was calculated by using the equation sigma maximum bending stress equal to mc divided by I. Next, to find the stress in beam, we have to make a few assumptions. The first one is we assume that the force applied to both ends of the beam is 50 Newton each, so that we can find the bending moments of the beam. If the force applied to both ends of the beam is 40 Newton, the bending moment will be 0. The next assumption we made is that the beam we use is the inner cylindrical part of the free body diagram. The outer cylindrical part is a cushion-made material to enhance the grip. The diameter and height of the beam are shown as below.
So for LO2, solving problems involving stresses in beams, we are going to determine the maximum bending stress in the let pull down bar. So here is the formula of the bending stress, which equals to M times C over I, where M is the bending moment, C is the perpendicular distance from the neutral axis, and I is the moment of inertia of the section area about the neutral axis. Now let's move on to the actual calculation part. Right, moving on. So here is the free body diagram of our let pull down bar. As you can see here in the middle, here is the neutral axis. To find C, as mentioned, C is the perpendicular distance or perpendicular distance from the neutral axis, or the Y, and that would be 2.76 over 2, which equals to 0.0138 meters. Then next, for the moment of inertia, we are going to be based on the formula of a circular cross-section, since we assume that our beam is our let pull down bar is a cylindrical beam, and the formula would be pi over 4 r to the power 4. And after inserting the value of r, we are going to obtain the moment of inertia of a value 2.848 times 10 to the power of negative 8 meter to the power 4. Then we proceed with the calculation of the bending moment. So as shown here, we set the moment equals to 0, and we also assume that anti-clockwise rotation is considered as the positive moment and vice versa. So for bending moment of the right hand side of the beam is equals to 80 newtons times the distance 0.190 meters minus 50 newton times the distance 0.384 meters, and that will equals to negative 3.84 newton meters, or it rotates in the clockwise rotation. So now we have all the required values, we can finally proceed to calculate the maximum bending stress. Finally, reaching the last part of the calculation. So based on the values that we found previously, we're just going to insert them in this equation right here. So negative 3.84 Newton meter, which is the bending moment, we multiply it with a C value of 0.0138 meter, and then we divide it with 2.848 times 10 to the power of negative 8, which is the value of the moment of inertia of a circular cross-section. And that will yield a maximum bending stress of 1.861 megapascal. So let's look at this diagram right here. So this is where the bending moment is applied, which is at the end of the beam. And lastly, this is the depiction of how the beam or the pull down bar will be bent as it is subjected to bending stresses.
Hi, I am Alia, and today I will prove that stress and deformation do exist in this light pull down machine. Let's start evaluating. The weight of a load applied on wire is 18 Newton, while the measured length of the steel wire is 2 meter, which is 2000 millimeter. The diameter of the wire as measured is 0.44 cm, which is 4.4 mm. As we know, the Young's modulus of the steel wire is 205 GPa, and the maximum allowable stress is 50 MPa. The steel wire is the one which connects the top end and the handle's end, which you can see in the picture attached. In order to calculate the stress of the steel wire, we need to take a cross-section part of the wire. Based on figure, we can clearly see the cross-section part. From the equilibrium analysis of the force in the y-axis, we can conclude that the force applied on the surface of the cross-section is 80 Newton. Next, to evaluate the stress of the steel wire, we need to apply the first formula as stated. The formula indicates that the stress can be calculated by dividing the force applied with the cross-section surface area. The cross-section surface area can be found by the second formula stated. Then, we should find the area first. After getting the area, we can now evaluate the stress of the steel wire using the first formula before. So, the stress is 5.26 MPa. Deformation of the steel wire also need to be evaluated. Here is the deformation formula numbered as 1. As stated, the Young's modulus for a steel wire is 205 GPa. From previous learning, we know that the Young's modulus formula is like this. From here, we can conclude that deformation is equal to stress times length of steel wire divided by the Young's modulus. So the deformation is 0.0513 mm. That's all from us. Thank you.